welcome to the second talk of this week. And today we have Professor Raychaudhuri with us, and I request Professor Mehta to chair the session.
Thank you, Joel. So it's a great pleasure to welcome Professor Sreerup Raychaudhuri, whom I have known for more than 2 decades. And, I think when my PhD journey started, this was the year 1999. He started at the IIT Kanpur around the same time, and I happened to be at HRI, so I used to see him often, and or hear about him from my fellow students. One of his students is a good friend of mine, Santosh. So I used to hear more about him also from Santosh and so on. But cutting the story short, let me just say a few words. He comes from the illustrious ARC family. Professor Amitabh Raychaudhuri, who was his advisor, and I think he happens to be somebody who has followed his passion and his interests at any given point of time. So it's slightly unconventional in that sense, but that is what something that connects with me. I really admire him for that. He was at IIT Kanpur when he loved teaching. He did the teaching. When he wanted to move out, he moved out to TIFR, back again. And then I think he has spent the longest period of time at TIFR, I guess, counting also his postdoc time. And lately, he has also been interested not only in theoretical particle physics, but also history of science, and also popularizing science, and discussing how things evolved in the Indian context and so on. And that all his lectures are available on YouTube, and all of those lectures are very mesmerizing, and it takes you back to those times and gives us a fairly clear idea about the development of particle physics, for example, and so on. So I think all his lectures, all his contributions in the form of publications, in the form of books, and so on. He has a very interesting book on extra dimensions. That time when the field was being developed, again, he came up with this book along with, I think, Professor Sridhar. And yeah, I think cutting the whole story short, I would not take any more time. I look forward to hearing from Professor Raychaudhuri on Lie groups and gauge theories in particle physics. I believe this is the second lecture in this series. So, yeah, stage.
So thank you very much, Poonam, for that very warm introduction. Maybe I should add something that I will soon, from next month, be moving back to a teaching institution. I will be joining BHU at Varanasi.
BHU.
So I'll be, yes.
Oh,
so
fantastic. Fantastic. So we should also get you sometime in person. And I should welcome you in real world also.
So I will be happy to talk to them. Happy to come visit. All right. So let me continue. So the last lecture, I will just quickly recollect. I talked about a U1 gauge theory, how to set up a U1 gauge theory. So that basically was the one which set up all the things for today's lecture. And how a U1 gauge theory, there is one physical system, which is a superconductor, where you can think of the U1 gauge symmetry being broken spontaneously, and then how to do that spontaneous breaking through a scalar, complex scalar, and with a specific self-interacting potential. So all of that I have described. Now today I will do all of that, but not with U1, but with a non-abelian gauge theory. So let me move on to, get rid of this somewhere now. This hide video panel, yes. Just a moment. I just want to hide the video panel because otherwise I can't. Okay. Hide floating. What is it now? Floating video. Okay. Yeah. All right. So today I will now start with non-abelian gauge theory. So then I'll try to make things as simple and straightforward as possible. So here we start with, instead of a scalar, one single scalar, complex scalar, we start with a scalar multiplet of length small n. So instead of one complex scalar, we have n number of complex scalars, which we put in as a column vector and that column vector I call capital phi. And using it, we can construct this, what we call the free Lagrangian density. So that will look like this, where this phi dagger, of course, will be the row vector with the phi stars. And notice that this thing, of course, if you multiply things out, it is just a shorthand for a separate typical complex scalar Lagrangian for all of the n's, just add it together. But the important thing is that they have a common mass. So mass degenerate free scalar fields put together gives you this particular Lagrangian density. All right, so this is the update of what I had written earlier, which was just one Lagrangian density, one term like this. If you remove the i's, you will get what I had in the last day's lecture. Now, let's consider not a U1 transformation, but an SUN transformation. So global, because the parameters will be constant, just like before. And so what that happens is that this phi column vector is multiplied by unitary matrix. So it's an SUN matrix, it's unitary, and as well as have determined U equals 1. And so that's how the matrix looks. And of course, that n doesn't have to be the same as capital N. Okay, it can be, but it can be different also. If it is, in general, small n has to be greater than capital N. So capital N is the n of the transform gauge group. And small n is the n of the representation. So if they are the equal, but now all these u's, of course, are constants with respect to space and time. That's why it's a global transformation. So the number of free parameters in an SUN matrix is the standard calculation. N squared number of elements, each is complex, so 2, minus n constraints, which come from the diagonal, from the magnitudes of each row, which is 1 from here, and 2n C2 from the fact that the dot products of these is 0. So 2 equations from each. And then 1, of course, from the determinant u being 1 condition. So you get n squared minus 1. So if it is SU2, then it's 4 squared, 2 squared minus 1, that's 3. If it's SU3, it's 3 squared minus 1, that's 9 minus 1, 8, and so on. Now, of course, we can also write this SUN transformation in the following way. Any unitary matrix, exponential Hermitian matrix. So it can be a Hermitian matrix where the thetas are all real parameters. And this dot product is not a scalar product in the normal rotation sense. It just means for writing theta, theta1, t1 plus theta2, t2, and so on. And the t's are the generators of un. Okay, so that's the way you can write this SUN transformation. And this is standard to any SUN. Mathematicians know this much better than I do. Okay, so under this gauge transformation, what happens to phi? Phi goes to u phi. Phi dagger will go to phi dagger u. And the Lagrangian density, let's see what happens to the Lagrangian density. This phi becomes u phi. Phi dagger becomes phi dagger u dagger. The u dagger u becomes 1. So d mu phi becomes d mu of u phi. And this becomes d mu of u phi. But u's are constants, so they can come out. The u's come out of the del mu. The u comes out of the del mu, and I can write it on this side. Remember, there's a dagger here, so that's where the dagger goes. And I have u dagger u. U dagger u, because it's unitary, is 1. So I get back the same Lagrangian. So that means this system of n mass degenerate free scalar fields possesses an SUN global gauge symmetry. And of course, if there's a gauge symmetry, we have seen that in Noether's theorem, then there are conserved charges. So here there will be not one conserved current, or there will be p number of conserved charges. What is p? P is the number of parameters in the gauge theory. This is p. This is p. Okay. Now the next step, as we have seen, we have argued that global gauge symmetry is not consistent with relativity. So we should have a local gauge symmetry. So the local gauge symmetry, all that we do is that we make these U's, the transformation matrix, a parameter, a function of space and time. So the X comes here. And now, as in the non-abelian case, you see that the Lagrangian density will no longer remain gauge invariant. So let's look at that. Same Lagrangian density with the phi primes. Now let me substitute the phi primes, remember? But now this U is local. So local means that the d mu is going to act on U. U cannot come just out of du like that. So I've just written this as two terms and this is two terms because there's one term where the d mu here, look at this one, where the d mu acts on phi and one term where it acts on u. So there are four terms here, out of which you could write it if you like by taking a u, you could pull a u dagger outside this and write the u dagger here. That's basically I pull the u out of this bracket and then it is u dagger, u dagger is 1. I can write it like this. But what happens is you have this 1 times, this is unit matrix, and there's u dagger u, which of course will go away, u dagger u, which will go away. So this term will remain unchanged. But here what will happen is that this d mu phi will give me this earlier thing. But now I have these extra terms. So there will be 3 extra terms, 2 cross terms and 1 direct term with the del mu u's, with the derivatives of the u's. And therefore, this is clearly not equal to the original Lagrangian. When will it be equal? If the u's become constant, all these del mu terms vanish, and then I'm back to the global symmetry. Now, of course, we have to have a solution because we need the gauge symmetry. We would like to have the gauge symmetry. So what do? We define a covariant derivative just as we did in the last U1 case. So the del mu picks up an IG, but instead of one field, now there's a matrix of gauge fields. So there's an n by n matrix of gauge fields. Because remember this d mu, this will act on a scalar vector of length n. So now, of course, all of these, in any case, mu is Hermitian. So these are not all independent, and we'll see how many independent ones we need. So we require the covariant derivative to transform exactly like the phi. That is, the d mu phi should go as u times d mu phi. For then, of course, if you rewrite the Lagrangian density like this as d mu phi, then the d mu phi is u and d mu phi dagger is has a u dagger. So the u dagger u then becomes 1. And it will be trivially gauged. So how do we ensure that this happens? Again, we do the same thing as we did in the abelian case, except that now we have to be by adjusting the transformation of the gauge field matrix. Of course, now we have to be a little careful because it's a matrix. So it's not, algebra is not as simple as the U1, but let's just go ahead and do it. So we want d mu phi to be d mu prime phi prime. So the d mu prime changes because the a changes. So therefore, it is 1 d mu plus g of a prime mu. And phi, of course, is u phi. All right, so I can write it as d mu of u phi plus I've just broken it up into 2 terms. So this we have seen, what is it? It is u times d mu phi plus d mu u times phi, and this is the same. Now I can put a u dagger here. There's no problem with that because it's 1. And I can put a u dagger here also because it's 1. So now there's a u on the left in all the terms. So I can pull a u on the left. I've taken that out. So u times 1, unity into del mu. And then I've taken the phi. There's a phi on the right for all of them. So phi is on the right. And whatever is in the middle, I have pulled it out. Then this has to be the same as d mu u. Plus this is we want this to remain unchanged, right? So it should be the same as this. So in that case, the 1 d mu is there. But this part should be Ig mu. So Ig mu is equal to Ig times whatever we have here. Ig, this one, plus this term. All right, so let's rewrite this as in this form. So I've just copied it. Now you could write it in the following by simply taking the Ig, this u dagger u to the other side, to Ig. So isolate this mu. Basically, remember, I want a transformation showing me that how is mu to be written in prime to be written in terms of mu. I have mu in terms of mu prime. So I need to invert this equation. That's very simple. I take it to that side. And then I write it like this, where I've taken now, so the Ig mu. So I multiplied by u and a u dagger, multiplied by u from the left, and multiplied by u dagger from the right. So now this mu has become clear, but the mu prime has become clear, but I have the mu will has this. Now note that u dagger is 1. So if you take the derivative, then del mu u dagger plus u times del mu u dagger is 0. So this del mu u dagger, if I take this to the other side, it's the same as u times del mu u dagger. Why do I want to do that? Because I want a u on the left. So I just do that. I just put this in place. So I have a U on the left. And then I want a U dagger on the right. So I just multiply by U dagger. So now here in both these terms, you see there's a U on the left, there's a U dagger on the right. So finally, if I plug that in here, a mu prime, there's a U here and a U dagger here. And inside, I have a mu minus, and of course I divide by ij throughout, so I'll get minus I by j del mu U dagger. So this is the equivalent of what we had in the abelian case, which was a mu, and there's a U dagger outside. So let's do that quick check. Suppose N R1, that means we have reduced to U1 gauge symmetry. Then U has this form, e to the minus ij theta, and mu is just, the matrix has just one number. So what happens to this? This just becomes that number. U is e to the minus ij theta. This is plus ij theta on this side. And here I have I by g del mu of this. So I just do the derivatives. And lo and behold, all these exponentials cancel out. And I have mu plus d mu theta, which is exactly what we had derived for the U1 case. So that shows that the formula is correct. Now, how many independent fields do we need? Remember here that this is supposed to, you take the U again to be like this. So U has P free parameters. So each free parameter will give me an extra term here, free independent term. And therefore, to cancel that number of independent terms, the A should have P independent fields. That's the requirement. So A should have the same number of fields as the rank of the Lie group. So this encourages us to expand A in terms of the generators. Because that's so we just use that. Generators are like a basis. And we expand A in terms of generators. And you can also write it like a dot product. Of course, only formally a scalar. It's like an inner product. Now, if you want to, you can plug this into this formula and work out the transformation properties of the end. Now, in general, this is pretty messy because the properties of the generators will come in, but we can do this for specific cases. We will. Now, we can also use this expression, short expression for E mu dot t, to write out the interaction terms of the Lagrangian density. So let's start from here. L has this form. So remember the d mu is the I d mu plus a mu, I j mu. And this a mu now I will replace by a mu dot t. So one term, of course, is just the del mu's on phi, del mu on phi. And then there's m squared phi. So I put all those together. That's the free scalar. Then here are the A terms. Ig, a mu minus I. So this is like a gauge scalar interaction. And this is similar to what we had as the current a mu interaction. And finally, there are the Seagull terms, which are the last two terms. A mu, and then there is phi dagger and phi on either side. So now, of course, we should complete the Lagrangian density by adding a kinetic term for the gauge fields. How do we do it? We write an F mu nu, which is the field strength tensor, but now it's a matrix. And we write it as minus Ig times the commutator of the two d mu's. So if we write the two d mu's as the commutator, you will get an expression like this. Of course, in the abelian case, U1 case, what happens? This commutator vanishes. So it's del mu nu minus del mu nu, which is what we had. So now we have, remember, how does d mu transform? It transforms with the u. So here phi, I could put u dagger phi if I wished. And then this u phi is phi prime. So d mu prime has to be u times d mu u dagger. So d mu goes to u d mu u dagger. So it's like a covariant. It is like a covariant derivative, as you expect. And then what happens to F mu nu? F mu nu has this form. So each of the d's will be like this. And if you multiply it out, what will happen? When you take the product of them, and you take d mu, then the u dagger and u will kill each other. You'll still have a u and a u dagger. U on the left, u dagger on the right. So you get this. And now, if you have to get gauge invariance, you have to multiply two F mu nu's, of course, for Lorentz invariance. So, but it's not enough because these are matrices. So you have to take the trace. If you take the trace, you will get a number. And then that, of course, is gauge invariant. Why the trace? Because once you take the trace, the u and u dagger, because the cyclic property, will touch each other. So the u dagger can be brought here and it will become 1. And the half, of course, is because eventually you will get trace of 1. This is like a 2 by 2 case, so that you will get half. Otherwise, it is 1 by n. Actually, this should be 1 by n. All right, now see here that in this product of F mu nu, there are products which have the del mu, nu type of terms, and there are products which have this, there are cross terms which have these mu, nu. So this mu, nu contains two A fields, and this contains one A field. So together these have three A fields. Similarly, this cross product will have three A fields. Now this one will have four A fields. So now instead of being free, you have actually self-interaction terms. So the ones with three A fields give you triple gauge vertices. The ones which have four A fields will give you quadruple, quartic gauge vertices. And these you won't have in an abelian gauge theory like QED, simply because this commutator vanishes. You'll have only these two terms, so there are no interaction terms. Okay, now let's look at the specific case of an SU2 gauge theory. What we did was for SUN. But for SU2 gauge theory, why did we go there? Because for weak interactions, we need three gauge bosons. We need a W plus, a W minus, and a W0. So this seems to indicate that we need a gauge theory with three generators. So the obvious one is to take is SU2. Because SU2 has three generators, it's the next smallest unitary group after U1. So now all of the above formalism will work, but except that you have to now take the generators of SU2, which happen to be half of the Pauli matrices. They are the Pauli matrices. And the Lie algebra is also simple. You have I, epsilon, ABC are the structure constants. So the full Lagrange has this form. I just copied what I had before. And now the phi, let us say, belongs to the fundamental representation. So it is of length 2, and we call the two elements phi A and phi B. And A mu is mu1 T1 plus mu2 T2 plus mu2 T3, where these are the three generators. What are the generators? I have defined them here. They're half of the Pauli matrices. So those are my A's. Now we can also expand the F mu nu in terms of these del mu's. And now, of course, you can write these. You can now extend each F mu can be defined as in terms of T1, T2, T3. So you'll have three, collect all the coefficients, and you'll have F1 mu nu, F2 mu nu, and that will look like this. So there are three coefficients of the T. So that can also be expanded. These are the terms. Each of them, remember, has this. Where did this come? It came from the commutator of two A's. So if you put T's inside, you'll get the commutator of two T's, and that's what gives you the structure constants. All right, now the next story will be, since we have got all this, let us see how to break this symmetry spontaneously if you want to break it. So to do that, we can now replace the scalar mass term as before by a potential which has a 5/4 interaction. So earlier this was phi star squared, phi star phi. Now it is phi dagger phi because there are many scalars in it. So this is a theory. Remember that this is a tachyonic mass. So it's a theory with n massless scalars and some self-interaction. So both of these are self-interaction terms. So we repeat the same idea. And as before, if we now define a real field, which is this eta, then the potential has this form, simply in terms of eta, with a local maxima equal to 0 and local minima at eta equals v by root 2, which is m squared by 2 lambda, same as before. However, these local minima correspond to phi dagger phi is eta squared. And now you recall that the phi has this form. It is phi A, phi B. So let's call phi A phi 1 plus I phi 2 by root 2, and they call this phi 3 plus I phi 4 by root 2. So phi dagger phi, what will that be? It will be mod phi A squared plus mod phi B squared. So 1 by root 2 will give me a half, and it is phi 1 squared, phi 2 squared, phi 3 squared, phi 4 squared. So therefore, the vacuum condition is that, this phi 1 squared, phi 2 squared, phi 3 squared, all of them will give you m squared by lambda. That's this one, this condition. So half of this is equal to m squared by 2 lambda. Half cancels, you get this is m squared by lambda, which is a constant. Now, of course, this is the equation of a force sphere. So earlier, what had we did have? We had phi 1 squared plus phi 2 squared was equal to v squared. So therefore, that was the equation of a circle, and I had drawn that circle. So on that circle, any point can be the vacuum. Now here, instead of circle, we have got a force sphere, and any point of that force sphere can be the vacuum. So what happens in physics, of course, in nature, only one of them is the vacuum, and the moment that happens, the symmetry seems to be lost. So where is it lost? It goes into, it basically goes to an ensemble, but we'll come to that ensemble later. So, by the way, it says the meeting is going to end in 10 minutes. So I hope there's a way to extend it. All right, so let me continue. So we had seen earlier that in the U1 gauge theory, the vacuum manifold, it's called a vacuum manifold. We are not going to use the properties of a manifold. We are not going to put up coordinate systems and so on. It's just a name. It's a set of all vacua. In the U1 theory is a circle. So here, what did we have? We had the scalar was phi1 plus I phi2. So that was like a complex plane. And it was traditional to orient the axis such that only phi1, this one, the real part had a vacuum expectation value. Right? This is what we had done. So if the point came here, we reoriented the axes like this, the phi1 and phi2, so that this axis came on the phi1. Now, then what did we do? We shifted the phi to this expectation of phi, which is v by root 2 plus phi prime. And phi prime was the proper field, which has a 0 at the vacuum. Now we are going to do the same thing in a SU2 gauge theory, in a force field. So the scalar field is lying like this. So therefore, that corresponds, the vacuum corresponds to a force sphere. Now I can't draw a force sphere, so I've drawn a 3 sphere and not shown the 4th axis. But once again, you have axes which are in arbitrary directions, and the vacuum is somewhere on that surface. So what do we do? So here, we do it in such a way that the phi 3 here has the vacuum expectation value. In other words, we rotate the axis so that the phi 3 axis passes through that point, which is the vacuum, and the others move correspondingly. So again, phi 4 axis is dropped. So only phi 3. So if we take the vacuum expectation value, it will only come in place of phi 3. So 0 and v by root 2. And now you shift phi by this particular vacuum expectation value column vector to plus a new phi. So with this, of course, you can write all the terms, but I'm only writing the Seagull term because that's the important one for me. So this is how the Seagull term looks. I'll have phi dagger phi. So the Seagull term, this phi changes to phi dagger, phi expectation value plus phi prime, and same on the other side. So there will be one term which has only these phi expectations. And if you take these, remember this is a constant. This is 0 v by root 2, 0 v by root 2, e squared. So this is a product of two A's. So clearly this is a mass term, okay, which has been generated by shifting the vacuum. So what is the mass term? This is the mass term. And you can write this, of course, as mu phi expectation into mu phi dagger, because remember mu is the same as mu dagger. Mu is Hermitian by construction. So let's expand this now. Expand this mu. See, what is mu? You expand this mu1. So 3 fields, 3 gauge fields, mu1, t1. So that is half, the t's are half sigma 1. So just plug the values for sigma 1, which is 0, 0, 1, 1, 0, sorry, 0, 1, 1, 0, minus I and plus I, and 3 is the diagonal thing. So this object, now I have these terms. Now I identify mu1 plus minus I mu2 by root 2 as W mu plus. I identify this as W mu minus. Of course, that is the complex conjugate, so it has to be minus. And this is a W mu 0. This mu3 is W mu 0. Let's see what happens as a result. So mu phi has these W's. You multiply it into v by root 2, you get v by root 2 W mu plus W mu naught. So mu dagger is this. And now if I multiply them out, what I get is the following. I get g squared v squared by 4 into W mu plus W mu minus, which is the mass term for a W, and g squared by 4, v squared by 4 into W mu naught, W mu naught. So notice something, that if you call half GV as MW, then this is MW squared, and this is half MW squared. Okay, but MW is half GV. Now, that half is fine because for a complex scalar, you don't have a half. For a real scalar, you have a half. So these are mass terms for the W's. So all the W's have got mass, the same mass. MW in this for the plus and minus, and also MW for 0. That half comes because in a real scalar, you always have a half. So now in this hidden gauge theory, we have shifted the phi. So I shifted phi, remember? So U1 gauge theory, how did you shift phi? You added this V by root 2 plus phi prime. So you have phi prime plus V. So when substitute the potential, now we saw that this led to a correct sign mass for phi 1, and also it keeps the phi 2 prime massless. So in the SU2 gauge theory, we'll similarly have a shift, and what it does is effectively you shift only the V by root 2. That means only phi 3 has shift of V. The others don't shift. So when you substitute back into the potential, you will get a correct sign mass for phi 3 prime, and the others will remain massless. So only the one which shifts gets the right sign mass, the others remain massless, and we call them Goldstone bosons, just like we had done in the abelian case. So we now have to worry about these three Goldstone bosons. So here again the Higgs mechanism works. I can remove them by making a gauge transformation beforehand. So just as before, you parameterize this phi matrix as e to the I psi into t 0 eta. Consider the unbroken Lagrangian density as before. And at this level, we are free to make any gauge choice because this is gauge invariant. So you make a gauge transformation, which is e to the minus ig theta, which is the gauge transformation, into this phi, which is e to the minus I psi t by eta. So here I have g theta minus psi dot t into 0 eta. This is a real field. Okay. Now, as before, we argue that since the gauge symmetry is going to be broken anyway, we might as well choose a special gauge. So you just choose the three gauge functions such that this term in the exponential vanishes. And that's what you've done here. And this is called the unitary gauge. So there are three thetas and three xi's. So you can just choose them suitably. Now what happens in this case, that exponential is gone, then phi becomes a 0 eta. So your Lagrangian has now we have only this phi eta. The ground state is still here, so you must still shift the eta. And once you shift the eta, what you will get is you will get the mass term, of course, you have already got for the gauge bosons. Your V, when you expand in terms of V by root 2 plus eta instead of eta alone, you will get the right sign for eta squared. So the mass of the eta will be twice m. And the Goldstone bosons will have disappeared. There's nothing else. If you had kept the xi, they would have been the Goldstone bosons. So again, I make the same argument that the W's have become massive and the Goldstone bosons have reappeared in the longitudinal polarizations now of these three fellows, of the W plus, W minus, and W. They have all become massive. And I have the thing. So earlier I had shown you one snake eating one egg and becoming very different. Now I have three snakes eating three eggs and of three different flavors. So therefore, I have masses for all the three weak interacting bosons. Now the gauge field matrix expands to the following. It expands to in the same, I've already shown that. So remember I had written the W's in terms of the A's. So let's now rewrite this in terms of the W's. If you do that, I've solved the A's in terms of W's. I've substituted the capital A mu in terms of W's. And now what you can do is you can take the coefficient of the W plus. So it is like W plus, W minus, and W naught or W3. And then these are the effective generators. So we call this T plus, these are the ladder operators for an SU2. T plus, T minus, and T3. And T plus minus are these. And of course, these also satisfy the Lie algebra of a certain kind. Now we've talked about scalars till now. Let me quickly introduce fermions. So it's very easy because like the fermions, you take a fermion doublet. And these are two mass degenerate Dirac fermions. Construct the free Lagrangian density as before. Okay. So we are introducing the fermions. So just like the scalar doublet, we will put in a fermion doublet. So where the two phis are two mass degenerate Dirac fermions. Having done that, now we construct the Lagrangian density as before. And we'll see now that if the psi goes to u psi, psi bar goes to u dagger psi, the Lagrangian density will be invariant. So once again, this Lagrangian density is invariant under global SU2 transformations. As before, we try to upgrade this to local SU2 by writing d mu instead of del mu. And then this d mu as before, invariance is now guaranteed. We've seen that, so I'm not bothering too much. Now, if you expand the covariant derivative, the Lagrangian density you will get is there will be this term for the free fermion. This, of course, is the free gauge part. And then you have to add on the interaction term, looks like this. So expand the interaction term, let's do that. So this A mu expands to W plus T plus W minus T minus and W0 T3. So there are three terms. There is a W mu plus couples to something with psi bar, gamma mu T plus psi bar, gamma mu T minus psi, and there's a T3 term. Sorry. So you can write this one. So W by this is the current corresponding to W mu plus. Current corresponding to W minus and current corresponding to 0. So these W pluses, so the Lagrangian as a whole has to be electrically neutral. So this is a charge current. It has a charge current of -1, remember. W mu has charge of +1. So the J mu minus has a charge of +1 and J mu 0 is neutral. So we have charged and neutral currents. If you write down the currents explicitly, let's look at J mu plus. I have put T plus here, and T plus was T1 plus I T2, so that's how it looks. And if you multiply it out, you will get psi A bar psi B. And J mu minus is psi B bar psi A. And finally, if you take J naught, it is psi A bar psi and psi B bar psi B bar. So very nice. So you have got the product of the different fields. So dissimilar fields for psi A, psi B for the charge currents and similar fields for the neutral currents. Okay, and the interaction Lagrangian now has this form in terms of charge and neutral currents. So you can write it out explicitly by writing all the currents. These are the charge current contributions. And these are the neutral current contributions. So the charge current contributions is a psi A, which is the A fermion being created. B fermion is destroyed, and there's a W mu plus. So you have a vertex like this, AB. Another vertex for the W naught, which is AA or BB. So W minus, of course, is the opposite of this. Notice that the coupling is roughly the same. Except for a factor of √2, which will always come with charge currents, it's almost the same coupling. Now, if I compare this with the intermediate vector boxes for the W mu plus, don't worry too much about that. But in that, I would like to identify the fermion doublet, let us say, either with the proton and neutron, or with the neutrino and electron, or with the neutrino and muon. So now, can we identify the W naught with the photon? I mean, that's the obvious thing to guess, right? That forgetting the fact that it has got a mass, because mass thing came only later. But can the W naught be the photon? So here is your answer. If the W plus minus are charged, then the W plus will transform like a negatively charged, positively charged object. This will transform like a negatively charged object. So therefore, if this term is to remain invariant, let everything transform. The W mu plus will transform with this minus e to the I theta. And these fermions will each transform with e to the I, where Q is the charge of the fermion. So now what we want is that this exponential should be 1 if it is neutral, which we want. Lagrangian has to be neutral. So in that case, the sum of these, so you see QA minus QB must be the same as 1. So then you will get a cancellation. So you require QA minus QB equals 1. But now if you look at the W naught vertices and consider them to be QED vertices, okay, so what are the W naught vertices? Here, W naught vertices have G by √2 and minus G by √2. So they have opposite signs. So one has to be the charge of A and one has to be the charge of B. So when we do that, so the W naught vertex, one has to be minus QAE and one has to be minus QBE. So that means that QA must be minus QB because, I mean, both are equal to G by √2, G by 2. So we have now solved the conditions. QA minus QB is 1, QA is minus QB. Result is QA is equal to minus QB equals half. Now, of course, these are not the charges, right? Because remember, we want to identify these either with proton and neutron, none of which have charge half, or with the neutron electron, none of them have charge half and minus half either. So the half and minus half is not enough. They are getting the same charge as the SU2 quantum numbers. So there are two alternatives. One is that A and B cannot be the Fermi particles, but in that case, This defeats the whole effort because we are trying to explain weak interactions. And the second is that the W mu naught maybe is not the photon at all. And that's already hinted by the fact that it picked up the same mass as the W's. Maybe it's a different particle. So the next question is, so what about electroweak unification? Why can't we just include the U1 group as a direct product with the SU2 group? So in that case, the transformation matrix would be like this, where T prime is the generator of U1 EM, and the direct product means that the T prime commutes with all the T's. Okay, we just include it as direct product. So that means there is an SU2 corresponding to weak interactions, there is U1 electromagnetic, and they don't talk to each other. So, okay, make the gauge field matrix, it will expand with one more term, which will have QE, and A mu will, of course, be the photon field. And we will give you interaction terms before. And so if you add them up, what you will get is the following. So working back, you can write this. So here are your interaction terms, W plus, W minus, and so on. So you can rewrite this in the following fashion, psi A bar, psi B gamma mu, into this particular matrix. And what is this matrix? This is nothing but G times mu dot T plus E mu T prime, where T prime is the one which diagonal comes from the diagonal. So QA and QB. So there is an E outside. I can take that common, but QA and QB, the two diagonal positions. The problem is that if this T prime has this form, QA, QB, then you can always write it like this, as QA plus QB by 2 into 1, and then T3, where T3 is, remember, 1 minus 1, because it's the Pauli matrix. So if that happens, then remember that QA minus QB is 1. So in that case, the T prime is, you can replace this QA plus QB as 2Q plus 1, and QA minus QB is 1. So half of T3. Now, what is my problem? Problem is that I wanted T prime to commute with all the TAs. But if T prime has a T3 in it, that will not commute with the T1 and T2. So I have a paradox. I mean, I started by assuming that the T prime commutes with everybody, but it doesn't. So Glashow pointed out that you cannot treat them just as separate direct product gauge theories. You have to make a common theory where both of them come out of that. And that is why you have electroweak unification. The root of that lies here, that you cannot treat them as direct product, as ununified theories. So what is Glashow's idea? So introduce a new U1, okay, which is different from the U1 electromagnetic, and it exists as a direct product with the SU2W. So the transformation matrix again will be the same as this, but now your T prime is like 1. It has to be unity, and this by construction will commute with all the T's. Okay, there's just some coefficient outside, which is W, and which is called hypercharge, but it doesn't matter. This by construction is going to commute with all the T's. So now go ahead and expand the gauge field matrix. This new U1 field we'll call B instead of A, and Y is some new quantum number which comes with it. So, and of course, it's a quantum number which comes, since this is a 2 by 2 matrix, Y is the same. It's multiplying 1. So it's the same for the upper and lower component. So it doesn't change with the which component you're taking. All right, Peter goes, go ahead and construct the gauge fermion interaction term as before. And I write the 3 terms here. I expand it exactly as before. And now what I get from here is the following. I get my psi A bar psi B into W plus, psi A and psi B bar psi A into W minus, which are all very good. Now here I will get the psi A is a combination of W0 and B, and psi B is a combination, again is a combination, orthogonal combinations of W and B. So Glashow says, now remember, I want something. I want to get the same couplings as I had before. So I need some more degree of freedom. So I assume that the W and B mix for some reason. He doesn't give you the reason. In 1961, there was no reason to assume, but he just said, let's assume that there are orthogonal combinations. So the W and B mix into two things which he called Z and A, and it mixes with the typical cos theta minus sin theta, cos theta, where W is, omega is some angle. We call it the weak mixing angle. Let's suppose it happens. In that case, the neutral currents, you can just plug in these. you can plug in the W and B in terms of Z and A, and that's done here in terms of Z and A. And now you see that if you want, you can make some of these couplings zero. For example, if you wish to identify A with the photon, we require to set this here. See, this is the coupling with the photon. You require to set this to the charge of the photon. Again, you want to, it has the charge of A. If this has to be the photon, then this has to be the charge of B. So you just plug that in the two cases. These are the charges of A and charges of B. And now you can solve for this. You can solve for G and G prime, and you find the following. Gs is equal to Qa minus Qb, and this is Qa plus Qb. Okay. Remember that Qa minus Qb was 1. So therefore, E is this minus Gs is E. So electric charge is minus G times sine omega. And if you plug that in here for the cosine, you will get G prime C by Y by Qa by Qb. So all right, so remember we have the freedom to choose Y. Y is some unknown. So choose Y is minus Qa minus Qb. In that case, this all cancels and I will get C and G prime. And therefore, G prime is G times tan omega. Notice that omega is some arbitrary angle, but it must be non-zero. Because if it is zero, then the electric charge becomes zero. You can't afford to have that. So we have this unknown angle. Otherwise, we have got all the correct couplings, and we have got some masses, and we'll see how the mass breaking happens. You could also obtain the relations for Qa and Qb, charges of A and B. They look like this: half plus Y by 2 minus half. Remember, when I didn't have Y, that Y term was 0, I had half and minus half. So now you have plus Y by 2 also added. And this, since these are eigenvalues of the T3 operator, you can write the general eigenvalues of the T3 operator plus Y by 2. And since this looks exactly like the Gell-Mann-Nishijima relation, which was obtained in flavor physics, you call this T3 the isospin, but you call it weak isospin. And Y you call the hypercharge, which is called weak hypercharge. It's a completely different quantum number. But since it looks similar, we use similar names. Now, this is Glashow when he actually did all this work. Now, this gauge theory works pretty well, and you give the correct coupling of the gauge up to the angle omega, which is not determined by the fermion sector. So how do we determine omega? And this was the great discovery of first of Salam and Ward, and then of Weinberg. So Salam's paper, of course, had many other things, so it was really confusing. Weinberg's paper is crystal clear. It is like a textbook. So both are attributed. So we go back to the gauge boson mass term. Okay, this was the Seagull term. And for the Glashow theory, we must include the U1 field in the gauge field matrix. In other words, you will have, see, this is the first three terms of what we got for SU2. Now we add on this U1 extra term with the B mu. So the B mu terms are added here. Okay, this is the unit T prime, remember, was the unit matrix with the Y. So the Y here, capital Y, is the hypercharge of the phi field. Okay. So now G times this into phi is this same matrix, A mu, into 0 B by root 2. So you multiply it out, W mu, and then this combination is there. And take the dagger, you get this. Multiply it out, you will get the similar terms, half GV squared, whole squared, W plus W minus, and then V by 2 root 2 into this. But now you have 4 terms here, because there are 2 terms for here, W naught plus B and W naught plus B, so 4 terms. What we can do with these 4 terms, let's look only at these 4 terms. Write it out explicitly, and now you realize that this can again written be, so you can't have this W naught B naught, okay? Because in a variable field theory, this will lead to mixing, it will lead to coupled equations of motion. You can't afford to have that. And anyway, even in a quantum theory, you would have to interpret it as a W suddenly turning into a B or a B suddenly turning into W, which can't happen. So you need to go to a basis where these cross terms don't exist. So you need to transform to orthogonal states with a cosine and sine. And now you choose what W as something, whatever cancels out those states. You use W to cancel out the cross terms. So rewrite it now as in this form, as a mass matrix. And you see this is a Hermitian matrix, real symmetric matrix actually. So if you diagonalize it, you put a diagonalizing matrix, which is exactly what we had. and tan omega is G prime Y over G. How to determine the capital Y? Again, write off the interaction terms. The lower component, remember, develops the vacuum expectation value, so it must be neutral. So minus half plus Y by 2. That means Y is equal to 1. It follows that G prime by G is minus tan omega. And if you take omega to be minus theta W, then theta W is known as the point value. It's the ratio of the G prime over G. And then eigenvalues of the mass matrix will, of course, look like this. Remember, this is my mass matrix. G squared G prime, Y is now 1. So G squared G prime Y, G prime squared. So look at this here. The determinant is 0. G squared G prime squared minus G prime whole squared. So determinant is 0. And the trace is G squared plus G prime squared. So what does that tell you? That one of the masses is 0 and the other is G squared plus G prime squared. Okay, so the determinant is 0. So that gives you 1 0 mass, which is the photon mass. And the other mass is mz squared, which will be G squared plus G prime squared. So if you plug in G prime squared by G squared and get tan squared theta W, you will get sec squared theta W, which means that mz is mw by cos theta. Okay, so mz is a little bigger than mw. And this is this beautiful thing, identification that, you get this mixing angle because of the diagonalization of the states. It is a symmetry breaking mechanism for the Higgs sector, which generates this mixing. And therefore, it gives you the correct unified theory. So last thing left is, how do we determine these parameters? You have the following equations. We have E squared by 4 pi is alpha. Since we know what E squared is, you can calculate alpha is 1 by 137. So that tells you what E is. Now, E is G sine theta W, MZ is MW or cos theta W, G prime is G tan theta W. So you can measure MZ and MW, that gives you cos theta W. And then that gives you sine theta W. So now you know what is G. And of course, you know theta W now and you know G, so prime, so you know G. So here are the experimental results. MW is about 80.4 GeV, MZ is 91.2 GeV, cos theta W is about 0.88, and that corresponds to 28 degrees 7 minutes. And these measurements of MW and MZ were first done by Kalarubia. He won the Nobel Prize for it. And then, of course, you can now calculate, use these equations and calculate. So E comes to be about 0.303. G, which is the weak interacting coupling, is about 0.642. You see, these are in the same ballpark. That shows you that the weak interaction and arithmetic influences are roughly the same. Weak interactions are weak because of these heavy masses. And G prime is also very close to the arithmetic coupling. So here are the 3 couplings of the electroweak standard model. Now, just to wind up, I just want to show you how good this theory is. Here is an experimental test of this theory. So the data points, the green ones and the blue ones and the red ones and magenta ones, correspond to various experimental data. And the standard model, the theory which you get out of this Gates theory, is the solid curve. And as you see, it works as a magnificent fit. And you can hardly have a better fit. It almost looks like you made it to fit those curves. But actually, this is separate theory and experiment are completely separate. And similarly, the final thing you needed to discover was that massless, that phi-3 boson, that was also discovered in 2002. And you see here a picture of this particular peak at 125 GeV is the Higgs boson. And now you see you have almost as much evidence for the Higgs boson as you have for the Z prime boson, which was discovered in the 1980s. So after this curve came, basically, that is when the Nobel Prize was given to Higgs and Englert. And that is basically our present state of knowledge. The standard model works. This electroweak unification theory works based on SU2 cross U1. So a semi-simple group. And yeah, so that's our understanding of electroweak interactions. So this, of course, a Higgs and Z resonances. And basically, that's all I have to say. So I conclude at this point. I will stop sharing and open to questions. So,
yeah, participants, if you have any questions, you can.
Not great, right?
I don't know how many participants are there today.
7, 8,
But
9, something like that.
I'm asking, sir, okay.
yes,
Please introduce yourself. This is Devendra, I think,
Which are
right?
not gauge field theory, right?
yes, Devendra, can you come back
Hello.
again? Yes,
Yeah. I'm Devendra.
yeah.
I was asking, there are quantum field theory which are not gauge field.
Which are
right?
not gauge fields?
Are there some important ones which are not gauge field?
Which are not gauge fields?
Are there important I don't know, but they are in general, sir, quantum field theory are not always gauge field, right?
Quantum fields are not always gauge fields. No. No, the gauge fields are the ones where there's a gauge transformation and when you are getting. So these are gauge. What I did in the last 2 days are gauge field theory.
But these things are those famous things that you're talking, they are all gauge field theory.
They're all gauge field theory. So our
Are
understanding
there
of the
important quantum field theory which are not gauge field theory? That I'm asking.
Yeah, there are many important quantum field theories, but the fundamental interactions are all described by gauge field theories. Okay, so the electroweak interaction, the strong interaction are described by gauge field theories. Now, gravity per se is not a gauge field theory, but weak gravity is. So if you take gravity in the weak limit, then you can expand it which is the linearized limit of gravity. Then it can be treated as a gauge field theory. However, when gravity becomes nonlinear, when it is strong, because Einstein's equations are nonlinear, then of course you neither know how to quantize it, nor is it a gauge. Does it have gauge invariance? It has general quantity invariance, which is a different kind of invariance. It's space-time invariance. Gauge theory is not a space-time invariance. It's an internal invariance where you make a transformation on the fields at the same space-time point. So it's not a space-time transformation. So what GR is one example of a fundamental interaction, which in the strong limit is not a gauge theory. But there are other gauge theories like 5-4 theories and so on. There's a whole bunch of many things, steering model, Kostelis-Thales model, and so on, which are field theories, but they are not gauge theories.
So I also think that this quantization of the gauge field theory is for certain topological regions.
You're very soft. I can't hear you. Louder.
Can you please repeat?
The quantization of the gauge field theory is for certain topological regions.
No, it is
of
possible.
The base manifold of the gauge.
Yeah, it's possible over the entire domain. The quantization is not an issue. It's possible.
Okay, so
It
way I
doesn't
see
happen.
that this invariance of the topological structure related to these charges and the
Yeah, so there are
called?
charges as I showed you explicitly. They correspond to topological structures. Yes, but it's not that the gauge field can be quantized anywhere. There are no special configurations where the quantization works and it doesn't work elsewhere.
Okay.
Of course, you can, if you want to do calculations in the gauge theory, you'll have to remain in the perturbative region. But that's how quantum field theory is always done. I mean, unless you quantize the free field, and then you treat all the interactions as perturbations. I mean, that's how you get all your Feynman rules and everything else. If it's a non-perturbative theory, then of course, you assume that there is quantization. You cannot prove it, because if it's a non-perturbative theory, some of the equations become, self-coupling is strong, and you get nonlinear equations. So then, of course, to do a field theory, to do any calculation, you have to go ab initio. You have to calculate the correlators from scratch, and that's what our lattice gauge theory people do. But then it has to be all done on the computer, because there is no analytic way of solving it.
Okay, thanks.
Okay, yeah. So unfortunately, we have lost most of the audience because of the Zoom.
Also, probably the live streaming could not happen. Is somebody watching
Yeah,
the
so
live
we will
streaming?
post the
Are there
YouTube.
any questions? It is not happening right now, right?
No, we could not do the live streaming.
We could not do. So,
Yeah.
so there will
Anyway,
not
you're
upload
going to
the
put
video
up
be
later.
any question.
You're going to
I
put
see.
up the recording. So
Yeah.
Yeah. So any questions people have, and which they may send you questions, so you can forward those to me. I'll try to respond to them as far as possible. Okay, so that's the best we can
This
do.
has been the problem with your talks. Last time also your talks has been many technical glitches.
Last time also what happened?
Many technical glitches in your talk. So YouTube voice is not there.
Yeah, I don't know. You have to do a better job, I'm afraid. I mean,
Yeah.
what can I do with my talk? I can only talk.
Yeah, it is our fault. I am asking.
Yes.
So it is happening with
Yeah,
us
yeah.
every time.
I think you need to improve that, because then the whole quality of the lecture, it suffers if something comes and something doesn't come. I will share my slides with you. At least the slides will be available.
Thanks.
And the slides will be available, and there's a lot of detail I worked out on the slides. So anybody who wants to work out details will get those details.
Yeah,
So,
perhaps they can post it on their webpage, the slides.
yes, I'll do that.
Also the recording. That would be
I'll do
helpful.
that. So,
Okay, then we will discuss.
Yeah.
Thanks, Poonam, for coming
So-
to share this.
Thank you.
Yeah.
Thank you for giving me this opportunity.
okay, thank you. It's nice to see you, Poonam.
Thank
after a long
you.
time.
Yeah.
And
Thank you
nice-
for
Yeah.
the nice talks.
Okay, thank you, Joel.
Thank you
And
for sharing
I
the
have,
session.
yes,
Yeah.
I have one talk left, which I will now give after about 2-3 weeks.
Okay,
And
sir.
that will be on grand unification. So in the same
Okay.
style as a non-abelian theory, how you can combine those and what
Mhm.
to do there. So that I'll give after some time, not immediately. So that I've had a discussion with them. Okay then, goodbye, good afternoon, and thank you.